This presentation introduces the concept of the structural archetype, which I am going to define as a characteristic of the form of a structure that affects its structural performance. The archetypes that I shall deal with are those that affect the efficiency with which material is used. All structures must have adequate strength and rigidity. Efficient structures achieve their required strength and rigidity with minimal input of material. Structural efficiency is crucial to the development of buildings that have a low embodied energy and low carbon footprint. A significant contributor to the carbon footprint of a building is the amount of material contained in its fabric and therefore in its structure, which in most cases is the major component of its fabric. The single most important factor that determines the mass of material required for a structure is its form, both its overall form and the detailed shapes of its elements in longitudinal profile and cross-section. The overall form determines the types and magnitudes of internal forces that occur within the structure, and the detailed shapes of the elements determine the efficiency with which these internal forces can be resisted. This is illustrated in this purely engineering structure, one of the bridges of Robert Mayer. This has a highly efficient structure due to three aspects of its shape. Firstly, the overall shape of its arch, which produces internal forces that are principally of the purely axial type. Secondly, the tapering profile of the arch, which matches the magnitudes of the internal forces. Thirdly, the cross-sectional shape of the arch, an inverted double T, which allows the internal forces to be resisted efficiently. These are examples of structural archetypes, which are simply aspects of shape which produce high efficiency. This section of the website is concerned with explaining what these aspects of shape are, why they are significant, and how they are used both in design and as a means of judging purely visually how a structure is likely to perform. To illustrate the effect of form on efficiency, let's look first at four very famous buildings: the Villa Savoye by Le Corbusier, the Sydney Opera House by Jorn Utzon, the Penguin Pool Ramps at London Zoo by Berthold Lubetkin, and the CNIT Exhibition Hall in Paris by Nicolas Esquillon. The efficiency with which material is used in these structures can be judged by considering the ratio of span to thickness of their principal structural elements. The relevant dimensions are given here, with the span to thickness ratios in the right-hand column, which ranges from 13 for the Villa Savoye to 1666 for the CNIT Exhibition Hall. These span to thickness ratios tell us how efficient the structures of these buildings are. Using these figures, and considering that the efficiency of the Villa Savoye structure is 1, the relative efficiencies are given here. The differences in efficiency are very large, with the CNIT shell being significantly more efficient than the other three. It is more than 100 times as efficient as the Villa Savoye and nearly 50 times more efficient than the Sydney Opera House. This enormous range in efficiency is principally due to the effect of overall form. The reason why overall form matters is because it determines the type of internal force which occurs in the structures when loads are applied to them. In the case of the Villa Savoye, the loads cause the horizontal parts of the structure to bend. When load is applied to the CNIT shell, the internal force is pure axial compression, and this is the essential difference, because, as will be shown in a later presentation, the presence of bending results in a large quantity of material having to be used to provide adequate strength and rigidity. Whereas if the internal forces are axial, these can be resisted with much less material, and we'll see why that is the case in one of the later presentations in this series. The important consideration is that the type of internal force that occurs is determined by the overall form of the structure in relation to the pattern of load that it carries, which is why overall form is such an important consideration so far as structural efficiency is concerned. Let's now look a little further into how this axial internal force only condition is achieved at the CNIT Exhibition Hall. To do that, we have to consider the load which the shell carries, which in this case is a distributed load caused principally by the weight of the shell itself. When the load comes onto the shell, the internal forces, indicated here by red arrows, are axial type internal forces. Let's look at that in a little more detail and consider an element of the shell and look at the way in which the internal forces and the shell interact with the loads that are being applied. This particular element is subjected firstly to the internal force from the part of the shell to its left, indicated here as a vector arrow whose length is directly proportional to the magnitude of the internal force. To this is added the vector representing the part of the load that acts on the element, and these two forces will produce a resultant. The resultant of the first two forces is transmitted to the part of the shell to the right, which supplies an equal and opposite reaction. Note that the second red arrow, representing the force going into the part of the shell to the right, is longer than the first, indicating that the internal force in the shell increases downwards towards the foundation, as one would expect. Note also that the direction of the second arrow is changed downwards, and this is a very important point because it means that if the axial internal force only condition is to be maintained, the direction of the shell must change by exactly the same amount. This little interaction of internal force and load is of course occurring all the way down the shell. Something that is also significant is that because the internal forces are increasing down towards the foundation, the lengths of the arrows representing them also increase, but the load arrow remains the same because the load is uniformly distributed. This means that the further down the shell that one goes, the smaller is the angle between the two red arrows in the vector diagram, which in turn means that the change in direction of the shell required to preserve the axial internal force only condition decreases. This is why, if we look at the profile of the shell in the photograph, the lower parts of the shell are less curved than the parts near the crown. The direction of the shell is changing quite rapidly at the top where there is a pronounced curvature, and this curvature diminishes in the lower parts of the shell where the internal forces are increasing, and the angle in the force diagram also decreases, and the shell becomes straighter. A very important consideration here is that to achieve an internal force that is pure axial compression, which is the necessary condition for high efficiency, the shape of the shell is not a free choice for the designer. It is determined by the basic physics of the system, specifically by the effect of gravity on mass. This is the significance of the structural archetype, which is the shape that preserves the axial internal force only condition. It accounts for the principal difference in efficiency between the CNIT shell and those of the Sydney Opera House. The archetype has not been followed in the case of the Sydney Opera House shell, and as a consequence, its freely determined form has produced internal forces that are predominantly of the bending rather than the axial type. This has resulted in a very inefficient use of material. Another example of the effect of form on internal force, and therefore efficiency, is given here. This is a reinforced concrete beam that spans 20 meters. Under typical loading, a depth of around 2 meters would be required to give it adequate strength. This would limit the stress in the material to an acceptable level. The internal force that generates the stress is affected by the form in quite significant ways, and we would find that if we introduced curvature by raising the centre of the beam by 1.25 meters, a depth of only 0.4 meters would be required to contain the stress within an acceptable level, due to the way in which the change in shape affected internal force. If we raised the centre further to 2.5 meters, the effect on internal force would be such that a depth of only 0.2 meters would be required. These three structures give an indication of the effect of form on efficiency. All three structures carry the same load. The lowest structure here is has 10 times less material and is 10 times more efficient than the straight beam at the top. This is a further demonstration of the effect of overall form on structural efficiency, because all three of these structures have the same strength. Quite small changes in geometry have a significant effect on efficiency. This is something that the designers of structures need to know about, and it is especially important if there is an intention to make structures that are of low embodied energy and low carbon footprint. The effect of cross-section is also demonstrated by a comparison between the CNIT shell and the Sydney Opera House. The CNIT shell is a hollow box made by two very thin skins of concrete separated by equally thin diaphragms. The cross-section of the Sydney Opera House is a fairly solid lump of concrete. Cross-sectional shape is another factor that affects efficiency. It is, generally speaking, the case that solid cross-sections, like the solid rectangular cross-section on the left here, are less efficient than more complicated geometries such as the I-shape or the hollow box. These are further examples of structural archetypes, and there is a presentation that explains why they have the properties that they do. The relative efficiencies of these buildings can be explained by their form. The form of the Villa Savoye produced only bending. The forms of the Sydney Opera House and Penguin Pool produced combinations of bending and axial internal force. The form of the CNIT shell produced only axial internal force. It was largely that was responsible for the enormous differences in efficiency. The fact that the first three of these structures had elements with solid cross-sections was an additional factor affecting efficiency. By looking at the shapes of structural elements in overall form, longitudinal profile, and cross-section, one can make a judgment concerning how efficient the structure is likely to be. This is the importance of structural archetypes, which is the subject of this section of the website. Knowledge of the archetypes and of their properties allows fairly quick judgments of structural efficiency to be made purely by visual inspection of the structure. Let's take finally another example of a famous building, the Centre Pompidou in Paris. Looking at the overall form of the building, it is rectilinear, similar in shape to the Villa Savoye. So the immediate response is to consider that this is going to be a rather inefficient structure. But looking at the longitudinal profiles of the principal elements, the main beams are triangulated in longitudinal profile, another archetype, which will improve their efficiency. And the Gerberat brackets are tapered in longitudinal profile and have I-shaped cross-sections. Both of these aspects of form will improve efficiency. So one's judgment about the efficiency of this particular structure is that it is basically an inefficient form, but that the efficiency has been improved by various aspects of longitudinal profile and cross-section to give an overall moderate level of efficiency. Certainly not a low-carbon form of architecture. So the conclusion of this introduction to structural archetypes is that the efficiency and therefore carbon footprint of a structure is highly dependent on all aspects of its form. The reasons why this is the case are explained in this section on structural archetypes. Knowledge and awareness of the archetypes and their effect on efficiency is essential for the design of buildings and indeed any object if it is to have a low carbon footprint.